Okay, so this is part of a question here. So let me just say this, that we're going to use the solar constant of 1360 watts per square meter. Okay, that's a 6. All right, and that's in the data packet. They say 1.36 times 10 to the third watts per square meter. Would it kill them to just say 1360? I just don't know. Okay. So show that the solar intensity of solar radiation at the orbit of Mars is about 600 watts per square meter, right? Well, how do we do that? Well, notice that it's farther. Mars is about 1.5 times the Earth's distance from the sun, right? Okay. So what we're going to do here is make this smaller. And remember, it's inverse squared, that the intensity is there's a formula in the packet that's totally useless, but it says intensity is proportional to x to the minus 2, right? So that just means that intensity is power divided by some constant, right? Some constant here, and it's x squared, right? Which really, don't we just know that that is actually power divided by 4 pi r squared, right? So then we get this, one of these tricky questions like, okay, well, if we increase it by 1.5, how does that work, right? The short answer, by the way, if you're just waiting for me to just tell you how you get the answer, you're just going to divide this by 1.5 squared. Okay, I'm just trying to explain, how you can get at that, right? Okay, so the intensity, let's see, we can go power over 4 pi, and I'll just say 1 squared, right? Or I'll say power divided by 1 squared times some constant is equal to 1360, right? The same constant, the same power divided by 1.5 squared equals question mark, right? So I'm just setting up a proportion, right? So basically I'm just using this, right? And I'm making the unit be whatever that distance is, right? So I'm saying k times, this is be the power output of the sun, right? Divided by the distance to the sun squared, right? So we know for us it's 1360, right? So then the question is, what is this, right? So you can divide these sides by each other. Well, k is the same, so that goes away. Power is the same, that goes away, right? And you end up with 1.5 squared over 1 squared equals 1360 over the intensity at Mars, right? So then how do we do this? Well, the intensity at Mars is just 1360 divided by 1.5 squared because of maths. All right. So this says, determine in K the mean surface temperature of Mars, assuming that Mars acts as a black body. All right. So we are going to do exactly the same thing. Now this Mars has almost no atmosphere, right? So we're going to ignore the albedo of the atmosphere. We're going to assume that energy, and by the way, the intensity of the radiation at Mars is, let me give you a clue what that number is. It is really close to 600 watts per square meter, okay? It's really close to 600 watts per square meter, right? So what we're going to do is we're just going to take that intensity that you get from here, the answer to this, right? That'll be the intensity at Mars, right? Okay, you're going to take that, and it's just the whole rotating planet type thing, right? So it's pi r squared. It's absorbed Mars. We absorb the energy on the frontal area is pi r squared, but we spread that out over 4 pi r squared. Okay, so it's going to be, we're going to divide by 4 pi r squared, right? And you'll get a number, okay? And that will give you the watts per square meter, right? The incoming intensity, right? The average intensity, right? I don't know what to call it. There it is, right? And then, okay, then you're going to do that trick where we set that equal to, I'm going to erase. Okay, so the intensity at Mars times pi r squared over 4 pi r squared, right? Okay, and that's going to give you some number, and that is a number between 150 and 160 watts per square meter. Okay, then what you're going to do is you're going to do that whole thing where we go, okay, the average intensity, I'll say IMA. Okay, so this is, I'll call this thing I Mars average, right? The intensity on Mars on averaged over the whole surface, the number that's between 150 and 160, right? Okay, that thing times the area of Mars, the surface area of Mars, is the total power output. That's going to equal to our input, right? This is our input. And then the output is going to be the emissivity, sigma, the area, surface area of Mars times the temperature to the fourth. Okay? Now, they say that Mars acts as a black body. So when they say that, they say that we're going to say it's a 1. A perfect black body has an emissivity of 1. So, and the surface area of Mars, we don't know its radius even, right? So we can't even do it, but it cancels, right? Okay. So essentially, you're going to say the average thing, the 1/4 of this number, right, is going to be sigma times temperature to the fourth. And I get a temperature that is between 220 kelvins and 230 kelvins, okay? And it rounds to one of those easily, okay? Then it says the atmosphere of Mars is composed mainly of carbon dioxide, has a pressure less than 1%. Outlined by the mean temperature of Earth is strongly affected by gases in its atmosphere, but Mars is not. Okay, so this is the greenhouse effect. I'm going to erase again in 3, 2, 1. Right? So the greenhouse effect again here, right, is that the Earth has this blanket of atmosphere. This is grossly exaggerated. The atmosphere of Earth is about as thick as a layer of varnish on a basketball. Don't want you to feel vulnerable about that, but yeah. Okay. Keep in mind that there are greenhouse gases in this atmosphere, right? Things like carbon dioxide, methane, whatever they use to expand, the gas that they put into the insulation of refrigerators is a greenhouse gas, right? And greenhouse gases will pass short wavelengths, and they absorb long wavelengths. This is key. Okay? So the sun is shining on the Earth. This is short wavelength. Why is it short wavelength? Because the wavelength of the light has to do with the black body spectrum, right? It's 2.90 times 10 to the minus 3 divided by the temperature. For the sun, this temperature is 5,800 kelvins. Right? So that's a big number. That's going to make this a short wavelength. Okay, so short wavelengths shine on the Earth. The Earth absorbs them. Okay, the Earth radiates long wavelengths. Why does the Earth radiate long wavelengths? Well, because again, it's 2.90 times 10 to the minus third divided by the temperature. But the temperature of the Earth is around 300 kelvins, right? 288 or something like that. Okay. And so, it's radiating infrared, okay? And the greenhouse gases in the atmosphere, especially if you have more of them, okay? And this is not the biggest hoax ever. It's actual science, okay? It absorbs those long wavelengths, and that warms the atmosphere. The atmosphere radiates the energy in all directions, but including back to Earth, okay? Mars, however, just basically has no atmosphere. It's like 1% of that of Earth, right? So really the atmosphere of Mars just can't do that because there's just not enough of it. Okay. Then that was one of the problems with the movie The Martian, or the book The Martian, is that there's a windstorm that knocks over something, or they're worried it'll knock something over. The biggest windstorm on Mars, you could barely feel the force that would exert. So I'm just saying. Yeah. All right.